Hello, everyone. Welcome to the webinar on Anoplophora kinesis of the Room 2 EU Priority Pest. So we are already 163 people at the moment. So thank you, everyone, for attending this webinar. As you might know, twice since last year, we have provided 3 webinars on the EFSA plan, Pest Survey Methodological Framework, and the toolkit, including the RIPEST and the OptiPest, and 4 webinars of the Group 1 Fruit Flies Streptidae. If you did not attend the previous webinars and you would like to know more about them, the recorded presentations are available on EFSA's YouTube channel and on the EU Academy website. This is the first webinar of our round of 3, and today's presentation will refer especially to the pest Anoplophora kinesis. Lastly, for the new attendees, as a reminder, since the microphones are mute, the Q&A chat is enabled for you to ask any questions that might come up while the experts are presenting. Before we start, I would like to remind some of the housekeeping rules. You are automatically connected to the audio broadcast, one-way audio, listening only mode. You cannot speak. This event is in English, and questions should be submitted in English by the Q&A chat. If some questions remain unanswered, you can resubmit them via email. This event is being recorded, and recordings will be published on the EFSA's official YouTube channel and in the EU Academy, and we will send all the information after this webinar. After the event, you will be requested to evaluate the EFSA's event filling out a Microsoft survey. As you must see in your screen, this is the agenda for today. So now we are in the introduction, and in a couple of minutes, well, 5 minutes or so, we will go for the real presentation with our experts. Today with us, we have Hans Tulke and Martin de Groot. And after their presentations, we will have a short quiz, as I told you, with the Mentimeter, just to evaluate if you understood this webinar. And by 11 o'clock, we will get to the end of this webinar. So who we are today? Today with us is, you might know him from previous webinars, is Hans Hermann Tulke. He is the lead scientist from the Helmond Center of Environmental Research. And also with us today is Martin de Groot. He's senior scientist at the Slovenian Forestry Institute. And my name is Jose Ovejas. I'm a journalist, and I will be the moderator of this webinar. So as I told you, this is the part where we have to use the Mentimeter. So as you can see in your screen, we would like to invite you to all participate in a poll to know who is in the room. Please proceed to search www.menti.com with your mobile phone or laptop. To participate, you can either use the QR code that you can see in your screen, or just put the code that you will see in the top of the screen. Before we begin with the poll, I would like to stress that Mentimeter will be also used at the end of the webinar to display several questions that the experts have prepared to check the understanding of the participants of the contents of this webinar. Therefore, it's advisable for you to keep this in mind and have an electronic device nearby to expedite the process. So let's start with the first poll. Okay, I see some of you are already responding this first poll. For those that are using www.menti.com, you can see the code in the upper side of the slide is 39843770. Well, I can see that most of you are from the National Plant Protection Organization. As I said, it's important you to know how to use this because we are going to use this application at the end of the webinar to check if you understood the presentation of our experts. So we reached to the moment of the presentation. So now it's the time to give the floor to our two experts. So Hans, Martin, the floor is yours.
Thank you. Good morning, Martin. Good morning, everybody in the room. Today we address a quite nicely looking insect, and we will go along this plan. So first of all, Martin will give us an introduction into the biology and the distribution of this beetle. Then we address in more detail the EFSA methodological framework, first starting with defining a target population if we want to survey this beetle. And then we do the statistical part to design the survey in repest. After, we will switch to repest and look what the answer is in terms of giving us numbers of inspections that we have to perform to detect the pest if it is arriving in our area of survey. So with this, we start this part one, and I hand over to Martin to introduce us the biology and the distribution of Anoplophora chinensis. Martin, please.
Thank you very much, Hans. As Hans already mentioned, I will present the biology and distribution of the citrus longhorn beetle, also known as Anoplophora chinensis. Next, you can find, I will not tell additional about ecology and about a lot of other information, but focus mainly on the biology. So if you want to have a lot of other information about it, I suggest you go to the pest survey card of the Anoplophora chinensis or the story maps. And if not anything else, the pest report to support the ranking of the EU candidate priority pest. Next. So the life history of Anoplophora chinensis is as following. So we have a larvae coming up in the tree, and it has already been developed. The adult will come, if you look at the one, it's coming out of the tree, and it starts to fly around, and then it's looking for a mate to another from the other sex to mate, and then to lay their eggs. That is in tree, and then it starts to the egg starts to develop in larvae and continue after a while to go into a pupae, and then afterwards, of course, it comes and it becomes an adult again and will fly out. So as I mentioned, there are four different development stages. So there's eggs, larvae, pupae, and adults. The duration of the eggs are 1 to 2 days, and it's in mainly you can find it in May to August, while the larvae the development is 1 to 2 years. This variability depends really on the climate. So if you look in the Mediterranean area, in the south of Europe, it is only 1 year. Well, let's say if you would go more into the north, you have 2 years. And you could find it the whole year round. The pupae is, the duration of the pupae is 8 to 53 days. And it's occurring in the winter or the following year. The adult has a survivability or is 30 to 70 days. And it starts in certain cases already in March, but mainly April, and then again a few individuals can be still found in December, but the main part is in April to August. Before the female comes out, of course, it cannot lay eggs straight away or fertile eggs. So the pre-oviposition period is actually 10 to 15 days. And the fecundity, which is actually how many eggs the female can lay, is 200 eggs. With that it's going to certain places, it lays only 1 egg per time. Lower development threshold of larvae is 20 degrees Celsius. And if we look at the larvae and how they are distributed in the tree, it is found, 90% is found below ground level. It is very problematic and invasive, especially because of its high polyphagy and the high reproductive potential. Next. So the origin of the species is mainly in the tropical area, especially in the south and southeast of Asia. It is invasive. It's present at the moment in 3 countries in Europe and in Asia, so in Italy and Croatia and in Turkey. It was also in other countries, but by that now it's already declared to be eradicated. On the EU, in the EU legislation, it is designated as Union Quarantine Pest and EU Priority Pest. So next. I also took the liberty to look what would happen in the future. Here you see a bioclimatic suitability map, which was prepared by Sao et al. And you see here for 2 models that actually Europe, especially the Western Europe and southern part of Europe, it's very suitable for this species. We are here mostly most problematic is the climate, because the hosts of the trees are available throughout Europe, but I will come back later on to that. Next. So if we're looking in the future with different scenarios, we see that in 2050 and also 2070 that actually we will have most of Europe being covered by both models, and that therefore this area is actually at risk to be that the species can occur over there. Next. Yeah, so what would that mean regarding economical impact? We have to look at crop loss. So the fact that the larvae goes into the wood would show dieback, reduced aesthetic functions of trees, which is especially problematic in urban areas. Next. Yeah, this species is a really interesting species. Unlike many species also on the list, this species has this is a polyphagous species. It's attacks more than 20 different families. You see a whole list of species, genera below, but the main genera where it occurs on is on maple, so acer, betula, birch, and on corylus. Next. The field, what should we be aware of? So we have to look at individual trees, so symptomatic trees, but also including recent fallen trees on the ground. We're looking for it the whole year because, let's say, a hole in the tree can be seen a whole year round, but it would be preferably looking for it in the flight period, which is from March till December. The symptoms and signs we have to be looking for is our tree dieback, round exit holes from 10 to 20 millimeters in diameter in the lower part of the stem and roots. Light brown frass at the exit holes and galleries in the wood where the diameter is 10 to 13 millimeters. Of course, the diagnostic signs are, of course, the individual cells itself. So looking for larvae, adult beetles, and this kind of things. And of course, there's if you find eaten leaves and shoot, this could also kind of indicate that there is a species there. So the next slide, Hans will introduce to the methodological framework, and the floor is yours, Hans.
Thank you, Martin, for making us aware of all the biological details, which we may need later to inform RIPEST with the necessary details, because we want to design a detection survey with RIPEST. So all of you may have had a look on this tool. So we will try to collect the information that we need to run a survey planning by RIPEST during the next slides. Those that were visiting other webinars already have seen this structuring of the target population that we have to do first, so that it's specified what we actually are looking for. And this structure has 4 levels that become more and more atomic until we know what the inspection unit is that in the survey will be the individual to address. First of all, we have to clarify what is the area that we want to survey, about which we want to have a final conclusion after using the survey design proposed by RIPEST in the field. So we have a particular area designed for these webinars, and that is Surveyland, somewhere near Madagascar, nicely placed and quite large, having an area of 78 million hectares. You will see this later. The survey area is what we want to conclude about at the end. So we have that overarching level. The next is one has to think about the epidemiological units that should be surveyed. And the epidemiological unit is characterized that we can assume that it is homogeneous with regard to the interactions between the pest, the host plants, the abiotic and biotic factors, but particularly also with regard to the management that is applied to the host plants or the pest in this area. So somehow this area is similar with regard to the infestation chance that we want to look for. So when we have the same epidemiology there, so we assume it is for all the Surveyland, is quite a large assumption to have the same structure over 78 million hectares. But when you apply this in other surveys, it should be a little bit more detailed with regard to this epidemiological unit aspect. Next level is risk factor. That means within the epidemiological unit, one might identify factors, processes, or activities that create in certain parts of this total population of the epidemiological unit an extra risk to find the pest. So this is particularly relevant if you have locations, geographic locations, where you can assume that an introduction of a pest that is not yet native in the area would happen. And why we are interested in these risk aspects, as you can imagine, if the probability to that the pest occurs exactly in this risk part, in the part of the population that we call risk population. If this probability is higher, then it would be more efficient to concentrate the search for the pest also in some way to these areas. So that means accounting for risk factors helps us to increase the efficiency of our applied numbers of inspections compared to a uniform random inspection effort. In our particular situation, we know from expert elicitations that we would expect to have the introduction with the import of plants into Surveyland. So we are expecting nurseries and garden centers as the places of introduction that then would provide in their surroundings a greater risk of or a greater chance to detect the pest if it is introduced. We have from expert knowledge elicitation already that the knowledge that the annual spread of this insect is expected to be up to 500 meters a year, which determines the area of greater risk that we can explore later. So now we are at the final atomic level of our target population, that is the inspection unit. This is the unit that we examine for the pest in different contexts with different methods, as it is listed here: trap area, plant inspection, plant part inspection, looking on commodities or the pest vector in other circumstances. And it defines us the minimum subdivision of the target population, by which we then can count the necessary inspections. And in our particular case, of course, as Martin was already explaining, how you find symptoms, you are addressing an individual tree. So our inspection unit is the individual tree. With that, we have reminded ourselves about the structuring of the target population, and we can turn to part 3. That gives us now the translation into the detailed input that we need to feed Ripest to make it possible to give us a survey plan at the end.
Okay, the first 3 items that we need to specify for Ripest are listed here, and we have to quantify them. That's what we will do next. First of all, we of course don't need to quantify the inspection unit, but we have discussed this already, that the inspection unit is the individual tree. However, we have to recognize that our pest is only interested in non-coniferous trees. So we have to remind that we have to exclude in our estimation of the number of the inspection units in the target population, the non-coniferous trees. So next we have to estimate the number of trees actually in Surveyland. To help with this, we have looked for parallels that we can use, and you see here 2 items that we propose that we can explore to calculate the potential number of trees in Surveyland. So we used the coverage with forest or the coverage with urban areas from Germany. So we have 33 that you see in orange to the left. We have 33% covered with forest in Germany and 15% covered with settlement and traffic area, usually addressed as the urban part of the country. But, and that's the green bit, we have to consider that of these trees, 49% are conifer trees. So we only use 51% of these trees for our purposes because coniferous trees are not a host of our pest. Now we know the area, and now we have to estimate how many trees are on each patch of this area. So we want to know how many trees of diameter larger than 10 centimeter, that's the request for our pest, are standing on a hectare of forest area or an hectare of urban area. And we use Martin's judgment on this. So he says that in a forested area, we have about 100 trees with a diameter larger than 10 centimeters, while in the urban area, where we also have our buildings and kindergartens, there is a little bit less, so we have 50 trees. This combination, this data we can now combine into a calculation for the number of trees. We do this in 2 steps, and to help with this, we have colored the different data according to the input that we just discussed. So the first part in the brackets is describing the number of trees in the forest area. So we have 0.33, 33%, times 100 trees per hectare for the forested area, times the total area of Surveyland, which was, as you have seen from the beginning already, 78 million hectares. And the same part comes, or the second part comes then from the urbanized area. So we have 15%, 0.15, times only 50 trees per hectare, but again, 78 million hectares of Surveyland. This is the total number of trees from which we only want to maintain 51%. This is the 0.55 that we multiply at the end to end up with the impressive number of 1.6 billion trees in Surveyland. So with that, we have the second information that we need, and we can turn next to the quantification of the risk levels. So as you have known, as you have heard before, the risk information is used to place our inspection effort with a greater effectivity according to the assumed higher risk of pest infestation of an area, and we are using the distance from the nursery. Could be also a garden center, but we name it nursery, so the entry points where the pest would enter into Surveyland. And we have, for Anoplophora chinensis, expert elicitation data that were determined in an EFSA expert knowledge elicitation in this year, quite new. And we have 2 distances with different risk levels assumed. The first one is the very narrow range of 100 meters, where the experts assume that the baseline risk is 7.7 times higher. That the risk inside this area is 7.7 times higher than the baseline risk. Then we have a second level risk area, which stretches from 100 meter distant to the nursery until 500, which is the estimated spread per year of the pest. In this, the experts assume that the risk for pest presence, or the risk of pest presence, is 4.5 times higher than in the baseline area. That is all around this blue circle. So we have 3 risk levels. In the middle, closest to the entry point, 7.7 times higher. We have an intermediary level, which is 4.5 times higher, and we have the surrounding basic level of 1. This is now the quantity of the relative risk. What we also must feed into ripest is the proportion of the trees, of the proportion of the target population, in our terms, the number of trees that are situated in either of these 3 risk categories. So how we can do this? We are using basically what we have done before. We are calculating the number of trees in a sub-area and then divide this by the total number of 1.6 billion trees to get the percentage of the target population that is in. For instance, for the risk level 3, we have this 100 meter circle. That means we have to calculate a circle with 100 meter radius, and you know it's P times R squared, radius squared. So we end up with a 3.14 hectare area that is around the nursery. Now we have not only one nursery, but probably in Surveyland there will be multiple nurseries. And we will try to estimate their number in the same way as we did it with the forest coverage. We look for Germany, where we have one nursery about every 24,000 hectares, sorry. And that means if we translate this into Surveyland, we end up with probably 3,250 nurseries. So around each of them, we have a 3.14 hectare sized high-risk area, which overall gives us 0.013% of the target population that is in risk level 3. When we do it now for risk level 2, that means we are taking the band from 100 meter to 500 meter, which ends up with around 75 hectare. You can calculate this yourself by estimating or by calculating the area of a circle with 500 meter and then subtract our 3.15 hectare. Then you will end up with this 75.4 hectare, multiplying this with 3,250 nurseries. Then we know at the end that of our target population, 0.314% is contained in risk level 3. And all the remaining, so we are subtracting 100% by the 2 percentages that we have calculated, we end up with 99.673% of the target population in the standard basic risk level. So in this regard, we have now done everything what we need to feed the risk data into Ripest, and I have summarized this here in the table. Our risk factor is proximity to the nursery as the only pathway we assume, and we have 3 risk levels with the relative risk of 1, 4.5 times, and 7.7 times, and the associated percentage of the area. Now we are finished with the target population. The next part of informing Ripest is addressing the statistically component. So why we need statistics in our consideration? That is very simple if you imagine that the perfect information about the pest status in a target population of 1.6 billion trees is achieved only by inspecting 1.6 billion trees. And now you will immediately oppose and say that's not practical. And indeed, that's true. And because this is not only a problem with our pest, but with many other pests, there were people that were thinking how we can solve this. And the idea is, as you can imagine, to consider a sample. The sample must have a sufficient designed size so that then afterwards, using statistics from the outcome of surveying this sample, one can conclude with a given confidence to the pest status of the rest of the population. That's the way how statistics comes into this framework that is developed by EFSA. At the end, by this, we will be told how many inspection units we have to examine by the protocol, and from where in the target population, remember the 3 risk levels in our situation, they have to be taken, so that we can probably conclude from the survey conclusion to the status in the rest of the population. Okay, so what data Ripest needs for this exercise? There are 4 design parameters because they are designing the statistically setting of this survey, sample-based survey. The first one is addressing sampling effectiveness and diagnostic sensitivity. And then we have to discuss the confidence level and the design parameters. Let's start with the first 2. These 2 are an important part of planning a survey, and they are informing us about the method sensitivity. The method sensitivity is meant to describe the probability by which the pest, by all the procedure that we are doing, is detected given it is present in the area that we are studying. This, of course, is a result of the combination of 2 processes. One is the sampling effectiveness in the field, where during the inspection, the pest has to be recognized in the inspection unit where the pest is contained. And then a certain sample that is brought into the laboratory for diagnostic confirmation. And then we have to understand what the diagnostic sensitivity of this laboratory procedure is. So we need the information for both of these processes to properly design our, or to properly inform RIPEST on it. So for this, we need an input from Martin, because so far we did not yet have seen this, but we have a slide for this, and in particular, I'm interested why the efficiency to detect the pest in the field is so low as 46% as shown here. Martin, can you help us with this and explain?
Yeah, I can, because as you can see, it's 46%. This was came out of the already mentioned EFSA expert knowledge elicitation, which was done in 2025. And yeah, they took into account the time that the larvae is occurring often below ground, as we already mentioned before, and that trees then don't often show the symptoms like dieback or something like this. So this is one of the things. And another thing is that trees are often very difficult to reach, and therefore that also made it that it's 46%. So, but still higher than the one from the sniffer dogs, which was 38.4%. Then we go to morphological and molecular identification of larvae. Yeah, then you have just larvae or an adult brought into the laboratory, and there it is actually quite easy. Therefore, the effectiveness is 90. They estimated it as 99%.
Okay, so we have now two critical parameters of RIPEST already quantified. That is the sampling effectiveness, which is very low in this case because we have to find very early stages of the infestation, which is not very simple with visual inspection. And we have knowledge about the diagnostic sensitivity once a sample is brought into the laboratory and inspected morphologically or molecularly. Both together give us the method sensitivity, which is calculated by RIPEST behind the scene. So we have finally to address two things, and that's the confidence level and the design prevalence. To remind what we are talking about here, we have this diagram put together, and we are now interested how they are relating to each other and how we can inform them. Let's start with the latter. So how we can inform the design prevalence and the confidence level. So there is no clear way to say it's like this, because both of these parameters are a managerial decision. They are deciding about the confidence into the final statement of the survey conclusion. And on the other side, with the design prevalence, this parameter is deciding about the pest risk that is still accepted before detection can happen with a certain confidence. So we see there is a balance between these two. And when we look on the diagram to the right, we can follow this trade-off between the two values. On the x-axis, you see how the number of inspection units tested or inspected is rising from 0 to 500. In color, you see a graph for the different design prevalence values from 0.05% to 1% to 5%. And on the y-axis to the left, you see the confidence level that is reached in a certain combination of design prevalence and sample size. So first of all, if we take one color into account and follow what the colored graph, let's say the green one, is doing when we raise the sample size. And you see how the line is growing, so that means the confidence into the survey conclusion is rising with the number of inspection units. On the other hand, if we are fixing our sample size or the number of inspections, let's say 200, then with the rising design prevalence, we see how the confidence level is increasing. So there we have this two-sided interaction. And now, what is the issue of the manager trade-off here? So when we take, if we are interested in a high confidence in our survey conclusion, then we would increase this confidence level by a larger effort of inspection numbers inspected, inspection units inspected. And when we are if we are keeping the design prevalence constant, so let's say, for instance, 1%. To lower the effort again, after doing this, we could increase the design prevalence, so we can relax the strength of our survey by saying a higher design prevalence is assumed. That means the detection potentially happens later with the same confidence, but with less number of samples. So there we really see how it is a trade-off between the two, and that's why we call it a managerial decision, because it combines the interest of safety and the interest of confidence. There is another way to think about design prevalence that could be the maximum prevalence of the pest in the survey area or the area the survey is addressing. That still can be eradicated. That still can be eradicated, for instance, by clear-cutting parts of the infested part of a forest. We will not follow this today, but there are other webinars where this approach is exploited. So now we have reminded sufficiently detailed about the interaction of confidence level and design prevalence. And for our survey, we are using the regulatory prescriptions. That is about 1% defined as the design prevalence. So 1% infested trees is the level from which on we want to have, with a certainty of 95%, a detection of the disease. That's the managerial design of this particular survey. Good. Now you see with this table that all the data is there so that we can jump to ripest. So I will bring you immediately there. Here you see the welcomes page of ripest, and we load a prepared survey that we did already, feeding all the data in so that you don't need to follow me putting in detailed names and numbers. And we can start. At the beginning of the ripest course to define our survey. So first of all, we have to specify the goal. So we want to comply with regulatory requirements. Then we have to determine the pest. You see what we have discussed, the pest name, that we assume it's absent. That's why we are doing a detection survey. When we have done our last survey and what this was done in 2024. Next, we have to specify our survey area, which is here already done by choosing Surveyland, choosing NUTS 1 as the selected unit. And here you also see the area of Surveyland in terms of 78 million hectares. Next, we have to say ripest whether we are what we know about the pest. So first of all, we have to specify what the target population consists. So which inspection units constitute to the target population. In our case, we have said that's the tree, or in words used in ripest is the plant. And then we have to specify all our host species, and we have to say whether the host population can be considered infinite. We will do this. No, we will not assume this because we want to apply risk factor calculations. For this, you cannot have an infinite population because you would not be able to determine these these small percentages that we have discussed before for risk level 3 and risk level 2. Therefore, we cannot use this approximation. Then we want to specify the epidemiological unit, as we have discussed this with the target population. We choose one epidemiological unit, assuming all the trees under the same management condition in Surveyland. And here you see the first data that we have to put in from our calculation. These are the 16 billion trees that we have in Surveyland in total, the non-coniferous trees that we have in Surveyland in total. Then the question of the risk factors is addressed by saying that we want to have a risk factor included in our consideration, and that this risk factor is dependent on the spread capacity. That we have to say because we have the data around the nursery and the distance potentially spread, including these two risk levels that we have. Then we say that we do not want to have a different risk factor. We have to specify where we will do our survey, basically everywhere where trees are. We have to specify the period for the survey, that is from March to November, as Martin was explaining before. And then we have to specify for the calculation of our method sensitivity, the methods for inspection in the field, and later the methods used in the laboratory. That's done by using that we have one method to do this in the field. That's a visual examination of the inspection units of the tree. And we are looking for signs of the pests, for instance, for frost. And we are checking in particular the branch and the trunk. And then we have learned from Martin that this process comes with an efficiency of 46%, which is even a little bit less than 50. So in the laboratory, that is then addressing the sample which is taken during the visual inspection for diagnostic evaluation. There we are considering a molecular method that is applying standard polymer PCR techniques. We're using the conditional PCR. And with that, it's quite clear that we have nearly 100%, but having a respect for the biological imprecision of everything we do in biology, there is 99 a safe assumption. This is important because the higher you are putting your sensitivity of the methods together, the less samples are taken. And if the assumption was too optimistic, you will miss one or two important samples in your sample design. So then we are in the design phase. As you remember, this is then the risk factor levels and the confidence level and the design prevalence. Yeah, so we have our confidence level set as 95% according to regulatory requirements, and we are using the proposed 1% as design prevalence. So far, so easy. Now we go to the risk factors. And remember, we have 3 levels of risk around the point of introduction. With the highest level, the first 100 meters around the point of introduction, having a relative risk of 7.7 times the basic one. And then we have the band around from 100 to 400 meters. That's the medium level, where we have found by expert elicitation this 4.5 times higher risk compared to the baseline area. And the baseline area has the risk level 1, the relative risk level 1. Now you see where we need our percentage of the target population that is in risk level 3 area, risk level 2 area, risk level 1 area. So you remember this is this value of 0.013, and then we have 0.0 0.314, and we have all the rest, which is 99% 673. In total, it has to be 100, and ripest will not help you cheating. So if I change this and I remove this 3, you see ripest is immediately opposing, so that you cannot put less than 100%. So all the target population is well distributed. And as we are doing a detection survey, we want to put most effort of the effort that we have to do according to statistical calculation of our survey sample. We want to put most efforts into the high risk area, so that because we are assuming there the greatest chance of the pest being, we want to have the highest effort to identify the pest there. That means we will put more convenience towards the high risk area. And this is expressed by these convenience factors, which are convenient. So they don't fit level 1, 2, 3. They are chosen as 1. In level 2, we want to have twice the one of level 1. And in level 3, we want to apply the threefold amount of the effort than in the basis level. This can be chosen in a different way. You can even concentrate everything into the high risk if you think that's more reasonable. So with that, we are at the point that we can ask ripest to give us an answer, and that's straightforward looking here. What is interesting, first of all, you see the target population side that is actually calculating the number of trees from our percentages backwards on this 1.6 million trees. That's easy to reproduce. And then we have to propose theoretical sample size, which by accident in our configuration gives us these nice numbers. Yeah, so it's really by chance, as we have chosen these. If you change one of them, they will change as well. So we have 60 samples in risk level 3, 40 samples in risk level 2, and 20 samples for risk level 1. That means in total we have 120 samples proposed. And with this individual confidence levels, when you join all the 3 risk areas together, then you have a combination of these confidence levels that leads us in total to a confidence of 95.14, as we have defined, because we want to have, with a 1% design prevalence, a confidence of more than 95% into the survey outcome if all of these samples would be negative. Then we could conclude that our area could be considered as pest-free. And that will be done if we put now in our survey result. But for the moment, we don't have a survey result. We are at the end of what we want to do. However, there is one issue. We want still to use ripest to tell us what would happen if we would ignore the risk dimensions. Yeah, if we go here, I go back to pages, and I simply switch off that I want to include risk aspects into my survey plan. So I'm ignoring the issue with nurseries. I now assume the pest drops everywhere, and the 1% of infested trees that I want to detect with 95% confidence by my survey are distributed well across Surveyland and not concentrated around nurseries. Then we can continue and we can simulate our results in a new way. And what we get out is that we now should sample 657 samples and distribute them randomly across Surveyland. And we receive a confidence level again of 95.02% this time. Okay, with this, we can go back and think about our very final slide, where we summarize what we have seen as information from ripest. On the left in the table, you see what the information that is listed. That is the confidence limit, that is the design prevalence, and the inspection units resulting after simulation from ripest. We have 2 different scenarios considered. First, we are using Surveyland without any risk structure. And the second, we are considering, or we are planning our survey considering the aspect of risk, of increased risk of pest presence around the points of introduction. with 3 risk levels, the first 100 meter and the 100 meter to 500 meter and the rest. The design prevalence, the confidence limit we say is 90, the requirement is 95%. The design prevalence is the same, also in both cases is this required 1%. And you see this 1% is corresponding to about 16 million infested trees then, which are distributed somewhere in Surveyland in the first scenario and around, potentially around our nurseries in the second example. And then the result line is the bottom of the table, which tells us that we have 657 samples without considering the risk factor, and only 120 are proposed when we are including the risk factor. So the difference is about 1/5. Yeah? So the number to sample is 5 times higher if we are ignoring or not exploiting the aspect of the risk concentration. So far, so good. The two estimations have some assumptions that have to be mentioned to be clear about this. One we have discussed sufficiently already. Without the risk structure, we have to consider that our infested trees should be randomly distributed across Surveyland, so not all in one point. And for the scenario with the risk included, we were combining the area of 3,250 nurseries that we estimated to be in Surveyland. And that means that they all should have quite similar infestation level. For information, we have put also one scenario that could be fit into Surveyland, where we consider only one epidemiological unit with one nursery. And then you can calculate correspondingly the data, and you can find the sample size that should be applied around one nursery to find 1% of the pest with 95% confidence level for this individual nursery. With that, we are at the end of what we want to show. And
we hope that you now are inspired to create your own survey for Anoplophora chinensis. And we thank you for your attention.
Thank you.
Thank you, Martin. Thank you, Hans, for your presentation. Now is the time to do a small quiz to test yourself and see if you've understood the webinar. So for this, we need to use the Mentimeter again. Please take your device and scan the QR code that you can see in the screen, or type www.menti.com on your browser and introduce the code that you can see at the top of the slide. So, as you can see in the slide, in the top, the code for this quiz is 18379235. So, the first question is, what is the pest status in the EU? For option 1, we have present in the majority of EU member states. Option B is a union quarantine pest. Option C is an EU priority pest. Option D, B and C are correct. I see lots of you are answering already. I give you a couple seconds for those who are trying to use Mentimeter for first time. Well, as I can see, most of you think the correct answer is the C. Let's see what the experts think at the end of their presentation. Okay, let's move to the second question. What is the managerial parameter of a survey design planning? Option A, design prevalence. Option B, confidence limit. Option C, both of them. Almost all of you think the correct option is the C, both of them. Some of you are divided between the others. Let's see what the expert think at the end of the presentation. Okay, so I give you a couple seconds to answer. Okay, let's move on to the third question. What is the main risk location for the introduction of Anoplophora chinensis? Option A, nurseries and garden centers. Option B, ports. Option C, private gardens. Wow, you were fast with this one. Almost all of you think it's the option A, nurseries and garden centers. Really fast on this one. Let's see if they are correct. So let's move on to the fourth question. How many different families of hosts are attacked? Option A, 1. Option B, more than 20 families. Option C, 15. Really fast on this one as well. And almost all of them think it's option B, more than 20 families. So let's move on to the last question, the fifth question. Where on the tree does the larvae occur? Option A, lower part of the stem and the roots. Option B, whole the tree. Option C, upper part of the stem and canopy. Again, all of you agree, almost all of you at the answer A, lower part of the stem and roots. Thank you all for participating in this quiz. We'll see now what Hans and Martin have to say about these answers.
Yes. Question 1, the correct answer was, according to the status, that the option D, where at least the one where both are in, it's as well a union quarantine pest as you treated as EU priority pest. And question 2, again, we had the option C as the result, combining both of them, because the design prevalence and the confidence limit are both chosen according to the objectives of the survey that has to be performed, and in our balance to each other in a trade-off between precision and safety versus the effort you have to invest.
So for question 3, it's what is the main risk location for the introduction of Anoplophora chinensis? It is option A, nurseries and garden centers. And then question 4, how many different families of hosts are attacked? The species is highly polyphagous, and so therefore it's option B, more than 20 families. And the last question is, where on the tree does the larvae occur? And that was, as everyone already, or most of you already agreed about, it's option A, on the lower part of the stem and in the roots.
Thank you again, Hans. Thank you again, Martin, for your presentation. Now we are getting to the end. Thank you all for attending today. We're glad to see that almost we reached 250 participants today. In case we did not manage to answer all your questions, you will find them published on the EU Academy. Please note that similar questions will be grouped where possible. We will send specific information. The recordings of today's event will be available on EFSA's YouTube channel and in the EU Academy with subtitles in 4 different languages: English, Spanish, French, and Arabic. Next webinars of the Group 2 will be on Anoplophora gravipenis, the 30th of September, and Anaeromia bungi, the 27th of October. Before we leave, please take a few minutes to scan the QR code on the right side of the slide. and fill in the evaluation survey. If you are unable to scan the QR code now, after this event, you will receive a link to access the Microsoft Survey form. Your feedback is essential to improve our future events, so please try to take a few seconds to do it. Thank you everyone for attending this webinar, and thank you once again, Hans and Martin, for your presentations. We have now reached the end of the session. I hope you have all learned about this pest and are now well informed about it. This is the first webinar after the summer break. As I mentioned in the previous slide, the next webinar is scheduled for September 30th. I hope you can all attend. Thank you.